We're going to start off this morning with a bell work, and I want you guys to classify the following as strong or weak acids and bases. So, take the knowledge that you learned from the last unit and apply it to this, and pause the screen if necessary so that you guys can start working. And when the substitute is giving you stamps, I would like for you to continue the video. That way we can answer the bell work. When you have labeled strong and weak acids and bases, the second part of the bell work would be to select one of these acids and bases and explain what might happen if you put them together. Some of you may know this already, but I want to see what you guys think. So the first one here, HCl, hydrochloric acid, is definitely a strong acid. Strontium hydroxide is a base because it has hydroxide in it, and it is a strong base. H2SO4 you should know as sulfuric acid, and that is a strong acid. NH3 is a base, and it is a weak base. So what happens when we mix acids and bases? Well, that's what we're going to learn about in this unit. We are going to specifically look at acid-base reactions, and we are going to see what the products are. So when we mix acids and bases, they do something called neutralize, and that's what Unit 15 is all about. We are going to talk about the mixing of acids and bases. Okay, most of the time these come in the form of double replacement reactions. So we're going to take a look back at one of the last units when we looked at reactions and recap on double replacement so we can be prepared for this one. Here in this picture, we're going to look and see that we're adding acids and bases, and depending on how much we add of each, it's kind of like a little scale. The more acid we add, the pH would fluctuate this way. The more base that we add would fluctuate in pH towards a greater value, towards 14. And so the word neutral in neutralization, we know that neutral means 7, and so we'll look at how this plays out in this unit. Neutralization reactions are the reactions of acids and bases, like I mentioned before. And their products here, what they form are salts and water. Okay, so a salt is going to be the result of an acid-base reaction. It's not the kind of salt that we think of, like table salt. It's a different kind of salt, and there's a lot of different kinds, but we know for sure that one of the products is salt of an acid-base reaction. The resulting solution is not necessarily neutral, so we can add different concentrations of different acids and bases, and we may get out a different concentration that's not necessarily neutral. We may form more ions in solution of H+, which would make it more acidic, or we may result with more hydroxide ions, which would make it more basic. So below here is the first example of an acid-base reaction. We have hydrochloric acid, and I'll use red for the acid, and I'll use blue for the base, sodium hydroxide. So when we mix these two, we form sodium chloride, table salt, and we also form H2O. So again, water is one of our products, and we form a salt. Okay, and a salt is usually something that contains a halogen, not necessarily, and some sort of metal ion. But real quick, let's recap on double replacement reactions. Okay, so the hydrogen here acts as a metal. It's got a +1 charge in the alkali metal group. It is going to swap with the other positively charged metal here. That's what double replacement reactions do. The negative ion, or the anion, is going to swap with the other anion, the other negative ion. Okay, so hydrogen and sodium will swap, chlorine and hydroxide will swap because they're both negative. And what happens is hydrogen will now be bound to hydroxide, and hydrogen has a plus charge. Hydroxide is one of those polyatomics that we memorized way back when, and these two will crisscross, and of course the +1 and the -1 will cancel, and we get something HOH, which we can rewrite as H2O. Our other products here, let's go over here. So sodium is now going to be with chlorine. And if we look, we need to make sure that the charge is crisscrossed. Sodium, alkali ion, has a +1 charge. Chlorine, a halogen, has a -1 charge. And again, when we crisscross these products, they are going to cancel out, which would leave us with sodium chloride. The last part is making sure that we have a balanced chemical equation, and it appears that we do, and if we needed to check, we could, but there are 2 hydrogens on both sides, 1 sodium and 1 chlorine. So we are it. This is done. This is how a neutralization reaction occurs. We add an acid and a base together, we get a salt, which has a metal ion and sometimes a halogen, and we get water. So we have 3 more examples that we're going to run through, and really all acid-base reactions are, again, is just double replacement reactions. We are having 2 compounds and we are switching the positive cation ions with each other to form water and a salt. That's the only thing that's consistent here, is that we have a water and a salt that's being produced. So we have sulfuric acid here, and we are being mixed in with sodium hydroxide, and so we are going to look and see what kind of salt we get, because we know we're going to get water somehow. We just need to figure out what salt we are going to get. So let's look at the swap here. Hydrogen, now it's not a metal, it's a non-metal, but again, hydrogen acts like a metal because it has a +1 charge. It's kind of a unique element. It will switch with the other positively charged cation here. Sulfate ion and hydroxide ion will switch as well because they are the negative anions. So hydrogen is going to come over here, and it is going to bind with hydroxide. Again, like we've seen before in the last slide, hydrogen has a +1, hydroxide has a -1. They cancel out when they crisscross to form HOH, or what we know as H2O. So there's our first product. And sulfate will bind with sodium when they switch. So sodium has a +1 charge. Sulfate has a -2 charge. And we know this now of 2 ways. Before, we memorized the polyatomics, and we knew that sulfate had a -2 charge. But now that we've looked at ionization, we know that sulfuric acid, H2SO4, can lose 2 hydrogens, and it can make it -2. So now we've connected these 2 standards here. When we crisscross sodium and sulfate, we will get Na2SO4. Okay, cool. And so what's going to happen is we need to balance, and that's where these 2's come from here. If you need to refresh on balancing, I suggest you go and watch Success 24/7. Let's move on to the next example. We have acetic acid, and it's combining with potassium hydroxide. And we're going to do the same thing. We're going to swap the positive cations, and we're going to swap the negative anions. And what we get, again, is water, and I don't think we need to show that again. It's right up here. But let's look at what happens with the other one. So acetic acid will ionize to form acetate, which is C2H3O2, and when that hydrogen fell off, it became a -1 charge. And potassium has a +1 charge, so here the charges are going to cancel. We want to make sure, though, that when we write these compounds, we put the metal first. Oh, excuse me. We want to note that we put the metal first. So let's see. We have water here, and then K comes first because it's the metal. We usually list the cation first. Potassium acetate, I believe, is how that is pronounced. Last example, H3PO4. We know that as phosphoric acid is being combined with sodium hydroxide. Let's swap our positive ions, and we will swap our negative ions. So hydrogen will combine with hydroxide to form H2O or HOH. And then phosphate. It has 3 ionization states. It is a triprotic acid. And so when phosphate combines with sodium. Sodium has a +1 charge. Phosphate, PO4, has a -3 charge. And when we crisscross, we will get Na3PO4. So let's move the box and see what we have. Nope, not the slide. Let's move the box. There we go. And Na3PO4. Okay, good. Pause the video, and you can rewind at any point necessary to maybe re-look over these examples. So I'm going to let you pause the video after you read this question. I want the video paused so that you have a chance to work out an example on your own. I want you to write the products of the reaction of nitric acid and potassium hydroxide. So pause the video now, and I'm going to work at it in just a second. Okay, so here we go. HNO3, and we are combining with potassium hydroxide. We will swap cations, and the anions will switch, and we will get water, H2O, and let's see. So I have potassium with a +1 charge, and I'm going to mix it with nitrate, which has 1 hydrogen. It's a monoproduct, so when it ionizes, it will have a -1 charge. Or you could just memorize those polyatomics from way back when, and you know that it has a -1 charge. So when those crisscross, they cancel, so it will be potassium nitrate, KNO3. Good. So continuing with notes, neutralization reactions are exothermic, meaning they have a negative delta H for enthalpy. They give off energy in the form of heat or light. They are spontaneous, which means that they would have a negative delta G, the Gibbs energy that we used to look at. And I'll write this in here, negative delta H. Titration is something that we are going to really focus on in this unit, and we will be doing a lab over this topic here. Titration is a process of adding one substance that we know everything about it. We know the concentration, we know the amount, and we are going to add it to a substance that we don't know, okay, an unknown concentration. And what's going to happen is, by doing this, by titrating this, what we call a standard solution, we are going to figure out the concentration of the unknown solution. So this is a way of identifying an unknown concentration of a substance. In neutralization reactions, we use indicators to help us determine something called the equivalence point. At the equivalence point, there's going to be a change in color of the indicator, and what this signals is the end of the reaction, because usually we know at what pH an indicator changes. We should be able to identify the indicators like bromothiamol blue and phenolphthalein. We just had a test on it on Friday, which most of you did very, very well. Okay. So let's label the parts of a burette. So a burette is an instrument that is used. A burette is an instrument that is used for a titration. We have this kind of long pipe. It can be glass, a plastic instrument, and there's a couple of labels that we want to throw on this instrument. So let's label. This would be called the stopper. Okay, this is a stopper. And what goes inside would be the standard solution. So the standard solution will go inside the burette, and we will stop the stopper. And what happens is we are going to take a flask. There's my best flask for you. It's got some lines on it. And we're going to take a liquid, and what's going to happen is we are going to fill this up with a standard solution, and we are going to drop it, and I know this isn't right underneath it, but we are going to be dropping this standard solution into something that we call the titrant. the titrant is what is being titrated. Okay, so that's going to be an important word for us, the titrant. So make sure we know this word right here, titrant. All right, so basically three things. We have the standard solution, the stopper, and the titrant. When we throw an acid into a basic solution or vice versa, the acid will contribute a hydrogen ion in the reaction. So that's what we learned last time with pH. When we have ionization, dissociation, a hydrogen breaks off and it floats around in solution. And when it floats around in solution, it becomes more acidic. Okay, so what's going to happen in a neutralization is we're going to have a hydroxide to counteract that hydrogen. And that's where we get the term neutral, right? If we cancel out that H+, that hydronium, okay, then we are going to become neutral. So an equivalent, okay, or what we talked about before, an equivalence point, okay, an equivalent is a mass of an acid or base that can furnish or accept 1 mole of H+. So again, basically, it's something that is going to equal 1. That would be like the first ionization. Sulfuric acid is diprotic. It has 2 hydrogens. So it's going to have 2 equivalents, right? So let's see if I can draw this on here. So H2, it has 2 equivalents of hydrogen, right? We are going to be able to get rid of not only 1, but 2 H+ ions. So we would say that it has 2 equivalents per mole. This means that it's going to take 2 hydroxide ions to cancel these out. Okay, so it would take 2 equivalents to cancel, or what we call here in this unit, neutralize. And one more question, and I'd like for the substitute to pause this question while we answer it. I'll read the question, I want you to pause it, and then when most people look like they're finished, we can continue. How many OH ions would be required to neutralize one single formula unit of H3PO4? Okay, so let's come back and let's figure this out. So H3PO4, and I'm thinking this is pretty obvious, but if not, let's look. H3, it's a triprotic acid, which means 3 H+ ions are going to bump out into the solution when this ionizes. It will ionize 3 times, and from what we know, we can write 3 ionizations, or 3 Kas, because this is what we learned, this is a weak acid. But that's besides the point. The question is, how many OH ions are required? Well, 3 OH ions will be required. And that completes notes for today. This unit is short, just like pH and OH was, but we are going to really focus hard on the neutralization reactions. We're also going to learn about something called buffers. Today, I want you to take the rest of the period, okay, and I want you to be working on worksheet number 1 of your homework packet. Okay. This will be stamped tomorrow. So make sure that you go ahead and do this tonight. Use the rest of class to work diligently and finish it up.